Assalamualaikum and hi to our lecturer, Dr. Nurhaliza. Our group consists of 4 members, namely me, I'm Hakim, Fakro Hadi, Amir Muklis, and Anis Mazat. In this video, we will give a detailed description of some application of software that involve the use of high performance and parallel computing in the real world. We have 4 sections in this video. First, this section will describe about what is HPPC in real life and its importance in the real world. The second is the application of HPPC in real life. This section will describe some applications that involve HPPC. Next is the conclusion. We will conclude what we can get through our research. And last but not least is the references, where all the reference materials that we use to make this research successfully.
So high performance parallel computing will also be used in real life application. So high performance computing is the ability to analyze data and conduct complex calculations at a rapid speeds. To put it into a perspective, a 3 GHz CPU on a laptop or a desktop computer can perform around 3 billion computations per second. While this is far faster than any person, it pales in contrast to HPC solutions that can execute quadrillions of calculations per second. Compute servers are networked together to form a cluster in order to create a high-performance computing architecture. On the cluster server, software programs and algorithms execute in parallel. A HPC cluster is made up of hundreds or thousands of networked compute machines. Each server is referred to as a node. Each cluster's nodes work in a parallel with one another, enhancing processing speed and also enabling high-performance computing. So to capture the output, the cluster is connected to the data storage, and these components will work together to execute a variety of activities in a seamless manner. Each component must keep up with the others in order to perform at its best. For example, the storage component must be able to feed and ingest data as quickly as it is processed to and from the compute servers.
HPPC on grid environments. Okay, there are some application requirements for the application of HPPC on grid environment. So the first one is that the system must be efficient management and transfer of terabytes of memory. Okay. The system requires an efficient management and transfer of terabytes of information and data in wide area distributed computing environments, and the example of features of such application is high energy physics, earthquake engineering, climate modeling, and astronomy. Okay, the second one is that the application must have a large sets of database, as it is shared by a community of hundreds or even 1,000 numbers of researchers worldwide. And lastly, in order to maintain the integrity and safety of the sensitive data, the features of the application must have user authentication and user control for the access of data. Okay, so this is the example of real-life application of HPPC on grid environment. The application is called data grid. So what is data grid? Data grid is a set of computers that directly interact with each other to coordinate the processing of large jobs, and all of the computers that involve are commonly spread across multiple geographically remote sites. So how does data grid works? There is a specialized software that will run in every participating computer in the grid. The software will act as a manager of the entire system and coordinates various tasks across the grid. Okay, as you can see on the picture, here are the data grid layers that shows all applications that are being connected either locally or remotely to one cloud that consists of many layers of the data grid. Okay, this is the data grid architecture. So at the lowest fabric level of the architecture are the basic components that makes up the grid, including storage system, networks, and computational system. So at the connectivity layers are various standard protocols for communication and security. At the resource level, are services associated with managing individual resources, for example, storage and catalog management protocol, as well as protocol for network and computation resource management. At the collective layer of the architecture, are higher level services that manage multiple underlying resources, including the replica management service that is the focus of this subject. Okay, so there are two application examples that influence the design of data grid service. The first one is high energy physics environments, and the second one is climate modeling. So what is high energy physics environment is that experimental physics application will operate on and generate large amounts of data. For example, we have Large Hadron Collider (LHC) at European Physics Center (CERN) that will produce a number of petabytes of raw and derived data every year for about 15 years. Okay, there are two types of data that is generated by the physics experiment, that is called the experimental data and the metadata. Okay, let's move on to climate modeling. Okay, climate modeling application will produce a large volumes of output, and it requires a lengthy simulation. This is happened because of the fact that the global climate change signal nature must be discernible above the noise of the natural variability of the climate system. The research group of climate modeling will generate large reference simulation at supercomputer center, and each simulation have a run span of 100 years. We see on cloud technologies. So application on the high performance parallel computing for cloud technologies have these following features. Okay, first, they can compute large instances. For example, cloud infrastructure services such as Amazon or GoGrid, it allows the user to provision complete cluster fairly easily and quickly by paying a monetary value only for the duration of the usage of resource. Okay. Besides that, the user has power to modify virtual machine. Okay, the user on cloud technologies can completely customize the virtual machine images and use them with root or administrative privileges. Okay, the last one is that they can build private cloud. Okay, what does it mean by that? Is that on cloud technologies, there are possibility of dynamically provisioning additional resource by leasing from commercial cloud infrastructures, makes the use of private clouds more promising. Okay, so for the following application of HPPC, there are two preconditions that need to be satisfied to perform large-scale data and to compute intensive application, which are the application should be parallelizable to utilize the available resources, and there should be an appropriate parallel runtime to support it. Okay, here are the example of cloud technologies of the current application. So the first one is Falcon, Hadoop, CGL MapReduce, Swarm, Dagman, and Dryad Link. Next, I'm going to talk about Hadoop and its detail as an example cloud technologies application. So what is Hadoop? Hadoop is an open source software framework for storing data and running application on cluster of commodity hardware. Hadoop also provides huge storage for various types of data, enormous processing power, and the ability to handle virtually limitless concurrent tasks or jobs. So how does it work? So there are 4 core modules that are included in the basic framework of Hadoop, which are Hadoop Common, Hadoop Distributed File System, commonly known as HDFS, yet another resource negotiator, Yarn, and MapReduce. Okay, so each of these core must play its own role to keep Hadoop functioning well. Okay, next move up to features of Hadoop. So first features of Hadoop is MapReduce as a programming model. Hadoop uses HDFLs to handle data. So point-to-point via HTTP as a method of communication, and Hadoop is implemented using Java, and other languages are supported via Hadoop Sumi. Okay, so what is the importance of Hadoop? Okay, The first one is computing power. Hadoop distributed computing model processes big data very quickly and fast. It is fault tolerant, which means that data and application are protected against hardware failure. And the last one is the fact that it is low cost. That means this open source framework is free and this uses commodity hardware to store large quantities of data. Part of the technologies application that I'm going to talk about is called Riot and Riot Link. So Riot and Riot Link are two Microsoft research projects that are developed to facilitate large data processing on computer cluster or data center for C# developer. So how it works is that the Riot runs sequential programs in parallel of cluster of computer on data center. So the parallel computation is organized as a directed acrylic graph where the program represents the graph vertices while the edges represent the communication channels between the program. Okay, you can see it on the graph. So the graph here shows that the relationship between the programs, where the inputs come from and where the output is directed to. It is must be acyclic to avoid program scheduling deadlocks. Okay, but the advantage of the graph is that it can be changed dynamically during runtime and is fault tolerant, and it can run on a single system for debugging purposes. Features that are in Riot and Riot Link. The first one is declarative programming, where computations are expressed in a high-level language that are very similar to SQL. The second one is type safety. That means that distributed computation are statically type checked. And the last one is integration with Visual Studio, where the programmer can take advantage of the comprehensive VS set of tools.
Next, I will be talking about the HPPC on the complex geometries. Complex geometries is the direct numerical simulation or DNS technique in which all the varieties and explicitly are resolved in time and space on the particular match that enabled by the high performance computing HPC. While still confined to the basic geometries, this technique allows to delve into the small aspect of the flow, resulting in a very detailed knowledge of the turbulence-related unstable flow phenomena. Due to the scale of the complexity of the problem, which is technology impact of the multiple component system, HPC application also indicate that the pre-processing and post-processing are two critical difficulties. So HPC solutions are used to solve a flow problem in complicated industrial system. Following that, a few industrial application for aircraft and combustion chamber application are discussed. This example provide the high-level overview of the numerical problem and the associated issues such as computing time, grid creation, and post-processing. So the first application is aeroelastic simulation that used in aircraft. This application needed a flexible wing design that interact with other components. Predicting the aeroelastic effort and time-dependent cycles such as flutter is important and required a lot of the computing power. In fact, to obtain a solution on the cost grid required around 150 to 350 gigabyte, putting a severe limitation on the hardware requirements. Large amount of memory is well suited to the parallel computing. In this context, high performance computing or HPC offer an intriguing approach for the simulating aeroelastic effect and design the next generation of the aircraft. Next is the simulation of the ignition stage of the chamber application. This application is used to demonstrate the capability of the modern large eddy simulation or LES algorithm in handling the complicated industrial setup. So numerical simulation can clearly show that LES can give the relevant data for the industrial setup, despite the fact that it is still in the demonstration stage. So the high number of the computing core is needed that may be required to generally define the size and kind of the problem being addressed. The completely transition LES of the ignition phase for the world helicopter gas turbine combustion chamber, for example, was realized owning the dedicated access to the world's most powerful supercomputer.
Firstly, I will explain about parallel computing big data analytics for solving real-life applications. Big data analytics is the process of forecasting large amount of data in order to improve prediction and visualization of real-world applications. The real-world application is a sophisticated system with massive data issues and extensive modeling. The goal of mathematical modeling is to make it simple to understand and recognize a system, as well as to find the best solution for predicting the pattern of the real-world application. As a result, parallel computing is the most efficient technique to solve a mathematical model using numerical schemes including massive sparse matrices and big data analytics. Below three example software of parallel computing. The first one is Parallel Virtual Machine (PVM), MATLAB Distributed Computing Server, and the last one is Compute Unified Device Architecture (CUDA). Parallel Virtual Machine. Parallel Virtual Machine is a software's heterogeneous computer system and unified structure of parallel programs that run in an easy manner on current hardware. Message routing, data transfer, and task scheduling are all handled by the PVM architecture's network. A library of standard functions enable task initiation and termination across a network, as well as global communication and task barrier synchronization. In this paper, the most recent version of PVM is PVM 3.4.6, which is integrated with the Linux Fedora Core 21 operating system. The PVM architecture is single instruction multiple data (SIMD). It proved by the single router connect to many clusters or devices. For the terminology, it implements master and slave, which the router as a master control more devices as a slave and serve as their hub communication. The second one is MATLAB Distributed Computing Server (MDCS). The MDCS is a heterogeneous computer cluster system with 8 workers running Red Hat Linux 2.6 as their operating system. The figure depicts MDCS distributed memory structures. Previous studies used distributed memory architecture to construct parallel algorithms. The MDCS use single instruction multiple data (SIMD) architecture. The parallel computing toolbox sends all the information to the job scheduler, which acts as an intermediary and generates a lot of data through the employee's computers. For the terminology, it implements server and clients whereby the host interact with the worker's computer, which is as a client. And the third one is Compute Unified Device Architecture (CUDA). The most recent parallel software is highlighted as Computer Unified Device Architecture (CUDA) as the parallel programming software in Windows 7 operation. A multiprocessor system or heterogeneous programming of CUDA software is implemented with ordinary C language to facilitate general-purpose computing on graphics programming unit, GPGPU, and simple application program interface (API) for managing device and memory. Shared memory architecture was used to develop the parallel algorithm. This parallel computing system uses single instruction multiple thread (SIMT) architecture. It adds multi-reading to SIMD, which improves efficiency by reducing the overhead of acquiring instructions. The term host and device are used in CUDA programming. Devices will be used to implement data parallelism. Both the Host and the device have their own memory, which is referred to as CPU memory and GPU memory, and is separated by the PCI Express bus.
So HPPC will also be used on AWS, which is the Amazon Web Service. AWS provides the most elastic and scalable cloud infrastructure to run the high-performance computing applications, and which allows us to innovate beyond the limitations of on-premises HPC infrastructure. AWS Parallel Cluster is also fully supported upon open source story, making it easy to deploy and manage HPC clusters in the cloud. AWS Batch enables you to run 100,000 of batch computing jobs. It also dynamically provisions the optimal quantity of compute resources based on the volume and requirements of the job submitted. Elastic Fabric Adapter complements the high networking requirements of tightly coupled MPI-based applications. It supports workloads that lower and more consistent network latency and throughput. In AWS, they were actually running wide range of HPC workloads, IBS every day, from the logistic and supply chain optimization to machine learning using Alexa. AWS also designing their own data centers and proprietary networks, as well as their own server design. They also have their own semiconductor team that designs chip for the next generation of in traffic to AWS. Some of the features of the HPPC on AWS is it is virtually unlimited infrastructure. In AWS, they have access to unlimited infrastructure, and it will allow you to scale on demand very quickly, and you will only pay for what you use. AWS enable this elasticity if you are 2 weeks late on a tape out, and you can scale your cluster in minutes to meet the deadlines. Also, the agility of AWS allows to iterate quickly and reduce time to results. AWS process will only take minutes, so we can quickly determine if you are using the right resources for the HPC workloads. And it also will increase collaboration with secure access to cluster around the world by using the global footprint with access to clusters from around the world. And this will result in a faster time to results and a better return on investment, which is ROI. It also have multiple clusters. In comparison, by looking at the running HPC workloads on premises versus with AWS, originally HPC systems have been one monolithic system with one queue and long wait times. As an example, if the R&D, which is the research and development, wanted to try something completely out of scope, they may have to wait for a long time before they can even see the results. So on AWS, it can have multiple clusters, and everybody will get the clusters, including production, R&D, and dev tests. If logistics need to run a forecast to determine the best and safest route for drivers, they also get their own clusters. At AWS, agility and scale enable HPC workloads to innovate in ways that never thought will be possible.